So the law of conservation of energy, the amount of energy before equals the amount of energy after. I can even be a bit more accurate. This is if we're ignoring friction and heat and sound and stuff that bleeds energy off. If I want to include that, I can even say it a little more accurately. I can go, or the amount of energy initial plus the amount of potential energy initial, so initial kinetic and initial potential, has to equal final kinetic, final potential, and if the numbers don't add up, whatever is missing must have gone into, Jacob, I'll call it heat. What I really mean is dissipative energies, energies that you lose stuff to, heat, sound, all that stuff. And this is going to be nice because this is going to actually let us be a little more accurate. Also, the other beautiful thing here is energy is a scalar. So this is a great way for us to analyze, Chris, curved paths and curved trajectories. Okay. Chris, do you skateboard? Okay. A great example of conservation of energy. Let me show you. So here is our mythical friction skateboard park, frictionless skateboard park for physics. I can take this skateboarder and I can give this skateboarder some potential energy. Did I raise their height? Okay. And if there's no friction, that will continue forever. Now, in real life, there is friction, so Jamie, this is just a simulation. But I want you to notice, if I actually show you the energies, which one of those isn't changing? The total energy you started with is what you're stuck with. But do you notice the other two are going up and down? Yes? When do you have maximum potential energy? When do you have minimum kinetic energy? Okay, so at the very, very top, right there, all of his kinetic has turned into potential. Where will all of his kinetic turn into, so where will all of his potential have turned into kinetic? The bottom. Okay. And the nice thing is, it doesn't even matter if this track has bumps and bends in it. For example, what if I go to this track here? Okay. Now, we're going to assume that the skateboard is magnetically glued to the track, so we're not going to get air. Otherwise, it's going to look a little weird. As long as I give this fella enough potential energy to clear that middle hill, we're good to go. And you can see if I go slow motion, here, right here, all of his potential has become kinetic. It all turns back into potential. Losing potential, speeding up, changing a kinetic. Gaining potential, slowing down. You haven't lost all of your kinetic there. You're still moving, but you've lost most of it. Lose all of it there. Let's go back to normal. I can, even if I want to, turn on friction. I can go real world on you. So if I go real world, we'll start off with our little bar graph. I'll move it to this side. Right now I have friction off. I'm going to turn friction on. Which energy do you see going up now? We call it heat. They call it thermal. This is why you can't go back and forth on a skateboard in a pipe without adding extra energy. So Chris, when you skateboarded, you kept going by adding energy from your body. That's what you do when you shift your weight, when you press down or relax with your legs. All you're doing is it's no longer a closed energy system. Oh, and where'd that energy come from? Because it's got to come from somewhere. What you ate, right? Stored energy in food. Okay.
But if you're snowboarding, the thermal go down?
If you're snowboarding, it's much less frictionless. Okay. So you don't lose as much to heat, but also you gain the potential energy not from your food, from the chairlift. In fact, a great example, roller coasters. We're going to look at roller coasters a little bit later. Roller coasters, that first little bump, that first hill, all that is, Sean, is giving you a whole bunch of potential energy to play with. Oh, and then we'll try and bleed it from you as excitingly as possible. We'll try and turn it into kinetic as excitingly as possible. That's all it is. Oh, and we'll grease the wheels down really, really well because we would prefer not to lose a bunch to friction. I wrote here Show marble energy transfer device. Swing set is a great example. On a swing, when do you have maximum potential energy? You've all been on a swing? Sorry? At the top, what's your kinetic at that moment for a split second? 0. Okay. When do you have maximum kinetic energy? At the bottom. How do you go higher? You add energy to the system, the same way Chris added energy when he was skateboarding. You add that by shifting your weight. You guys have all learned how to know, kids never get taught how to do a swing. You figure it out, right? It's a great example of conservation of energy. You're not violating the law of conservation of energy when you're going higher and higher. You have to do work yourself. You've added energy to the system. So, let's look at some examples. Back to the notes. A projectile is launched straight up into the air, I wrote. If its initial velocity was 84.3 meters per second, how high did it go? Use energy and ignore air friction. Now, we could solve this using Vf equals Vi plus At and D equals Vit plus a half At squared and all those, but you can also solve this quite nicely using energies. Now, I forgot to give you one piece of information, so we're going to add here that the mass is 55 kilograms. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Plus heat? Oh no, it says ignore friction, does it not? Kinetic energy, that's a half mv squared. So I think kinetic energy initial would be a half mv initial squared. Right? Plus potential energy is mgh. I think potential energy initial, Roy, would be mgh initial. Yes, Greg? Gonna make it? Equals a half mv final squared plus mgh final. Right? Are any of these 0? Let's see. Does this question say that you started at rest? No.
Why do you do half of that?
That's the equation for kinetic energy. It's a half mv squared. Just where it's on your formula sheet, you'll memorize it, but that's the equation for kinetic energy. It just is. I didn't do a proof, I just said here it is, but trust me, it is. So you're not starting at rest? How high are you starting? I think on the ground? Are we not? Oh, and at the top, final, how fast are you traveling for a split second? Two of those values in this case are 0. Your initial potential and your final kinetic. So I get this, a half mv initial squared equals mgh final. Oh! I see something else. Anybody see it? Something cancels. The mass and everything. Turns out I didn't need to give you the mass. I thought I had to. I said it's 55. Turns out it doesn't matter how heavy the object is that you launch. If you're ignoring air resistance, anything that you launch at 84.3 meters per second will reach the same height, whether it's a baseball or a cannonball or a semi-truck. What's this question asking us to find? Which is how high in my equation right now? What variable is that? H, get the H by itself. How? Okay, divide by G. So we're going to get this. The final height is equal to VI squared divided by G. And Nick, instead of a 1/2 in the front, I'm just going to put a 2 down there because multiplying by a half, same as dividing by 2, but I think you'll agree that looks prettier, less intimidating. Not as ugly. What's VI? 84.3 squared all over 2 energy, scalar or vector? So don't put a negative. Just plain old 9.8. If we ignore air resistance, how high will this get? Ooh, that's a good height. Let me see. It sounds about right.
Yeah.
362.576. So yeah, 363 meters sounds good to me. B. Suppose the projectile only reaches a height of, I wrote 72. Can you put a 1 in front of the 72, make it 172 meters? How much work did the air friction do on the way up? Brad, is this question now talking about friction? Okay, so we're going to use conservation of energy. K E initial plus P E initial equals K E final plus P E final. But Brad, we're going to say whatever's missing must have gone into heat. That's air friction. And sound and air resistance, but I'll lump them all together as just one thing. That was our second version of this conservation of energy equation. Are any of these 0? Let's see. Are you starting out at rest? Nope. Are you starting out on the ground?
Yeah, probably.
Did we start out on the ground in part A? Is part B the same question, but I just told you it didn't go as high as we thought? Are we starting out on the ground?
Yeah.
Are we coming to a stop at the top for a split second? At the top, are we on the ground? That's a dumb question, but that's not going to cancel. Plus heat. Enzo, what's this question wanting me to find? Ah, let's get the heat by itself. How would I get the heat by itself?
Minus the PE final.
So if I hear you, Enzo, and I think I do, what you're saying is heat equals KE initial minus PE final? I would agree. Chris finds that so amazing he has to stretch. I agree. Chris, this is going to look like this then. Heat equals KE is a half mv initial squared minus mgh final. Do the masses cancel this time? Nuh-uh. Wait a minute, Mr. Dewick. I see an M there and I see an M there. Why don't the M's cancel? Do you see an M here? Now you know why they don't cancel. No mass and heat. So I guess I did need to give you the mass after all of 55. Let's plug and chug. Instead of 1/2, you know what I'm going to type on my calculator? 0.5. Times M, 55. Times V initial, 84.3 squared. Minus M, 55. G, 9.8. final height, which I thought was 363, turned out to be 172. How much energy went into heating up air molecules, moving them around, giving our kinetic energy to the air molecules, the sound that you heard, all the dissipative energies, the energies that steal from our system? A fair bit, because it went barely half as high as originally. Do you get 102,720.475? How about 103,000 if I go to 3 sig figs? You were right. Units. Heat's energy. Joules. Someone earlier brought up snowboarding, skiing. Hey, great, let's look at snowboarding, skiing, example 4. So at location Z, we happen to know that this 72 kilogram skier is traveling at 18 meters a second. How high up the next slope can the skier reach? This is where energy really shines, because his velocity, his speed right now is horizontal, but we're finding out how high vertically. You can't do that with D equals VIT plus a half AT squared with VF equals, remember, everything had to be in the same direction. We had to be really fussy on our vector notation. So in fact, Jordan, here is what I ask myself. If I'm trying to decide, would this be better to solve using conservation of energy, or would this be better to solve using unit 1? I ask myself the following little soliloquy, the following little set of questions. Look at this question, Jordan. Is there a change in height?
Yeah.
Is there a change in speed?
Yeah.
Is it a curvy path, not a nice straight line? This is a job for conservation of energy. Is there a change in height? Yep. Is there a change in speed? It's going to slow down. Is it a curvy, funky path? Yep. This is the job for conservation of energy. This is a job for a scalar approach. Plus heat?
Yeah.
So let me ask you again, Cole. Plus heat? No. And you know what? I think on snow, this would be reasonably accurate. Is there friction on snow? Some, but certainly not as much as on gravel. Yep. I'm not doing perfect physics right now. We're back in our imaginary physics world, but at least this is better than doing this on gravel, let's say. Are any of these 0? So initial is location Z. Is he at rest at location Z? Does he have no kinetic energy? No. How high is he at location Z? Oh. Final. At the top, how fast will he be traveling when he gets to the top? Oh. How high will he be at the top? That's what they're asking me to find. Let's assume it ain't 0. So those two cancel. This is going to be a half m v initial squared equals m g h final. Oh! Huh. What do you notice? Turns out, even though the question gave me the mass, by the way, the fact that the mass cancels explains why little kids can ski with grown-ups. Otherwise, either the kids or the grown-ups would have to be constantly making adjustments, You don't. There is a little bit of friction, so the masses technically in real life, Aaron, don't quite cancel, but it's close enough that a 5-year-old can ski with his dad without too much difficulty, without having to do too much adjustments. Oh, never thought of that, but yeah. Hey, what are they asking me to find here? Let's get the h by itself. How? Oh, it's going to be the same. We saw this earlier. It's going to be VI squared. There's going to be divide by G. And instead of times by half, I'll put a 2 down there, Roy. That looks prettier. Yes? What was V initial? 18 squared all over 2 times 9.8. Oh, by the way, make sure you notice there's 2 numbers in the denominator, so put the whole thing in brackets. About 16.5 meters up. Here's the nice thing. Again, energy is a scalar. What if, instead of this hill, don't write this down, what if the hill was really, really steep like that? Doesn't matter. They'd still reach 16.5 meters in height. Or what if the hill was really, 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 really shallow like that? Doesn't matter. They'd still reach 16.5 meters in height. Well, energy is a scalar. It doesn't care about the direction that you took to get there. All it cares about is before and after.
Would it change the real world? In the real world, wouldn't it go a little less high on a long slope because you'd have more time for friction to work on it?
Probably, yeah. Yeah.
Also, why did you put 2 gravity?
What's sitting right there? Read it out to me. What number's right there?
0.5.
No, it's not what's right there. Exactly. Read it out. Huh?
1/2.
Instead of multiplying by a half, isn't that the same as just dividing by 2? And doesn't that look cleaner? That's why. Nick, do you ever have deja vu? Do you ever have deja vu? I think I said that to you about 5 minutes. That's okay. Cole's back with us. Hey, skiing, nice. You know where this really shines? This is where I'm nuts. This is what I love about the physics. Roller coasters, baby. Roller coasters. How many of you have been on a roller coaster? Okay. Chris, the whole point of that first hill is give you as much potential energy as possible and then turn it into kinetic. And yes, there is some sound and there is some friction, but let's assume they really grease this sucker down so that we're pretty good. We have a roller coaster. It's traveling as shown below. So this clearly isn't the first. Oh, I guess on the first hill, by the way, you don't quite have zero kinetic energy because you are moving slowly over that first hill. So it gives you potential and a tiny bit of kinetic, right? That chain does keep you moving. But on the rest of the hills, you've got some good kinetic energy. Even at the top, often you're going pretty fast. So here's an example. We're on the second or third hill. At the top of the hill, Greg, how fast are they traveling according to this question at the top of the hill? Look at the diagram. 12 meters per second. We want to figure out, hey, how fast are they going at the bottom, location B? If we ignore friction. Jordan, you ready? Is there a change in height?
Yes.
Is there a change in speed?
Yeah.
Is this a curvy, wonky path?
Yeah.
This is a job for conservation of energy. Cold plus heat? No, it says ignore friction, so we will. Are any of these 0? Is our initial speed at location A 0?
No.
Is our initial height at location A 0? Is our final speed at location B 0? Is our final height at location B 0? Woohoo! Hopefully you've reached the point where anytime you can cross something out, hey, I like that. My little math nerd heart goes a little bit of pitter-pat. So really, I can write this as, Nick, what was the equation for kinetic energy?
Half mv.
Yeah. Not a half mv squared, don't forget the squared. Half mv initial squared plus mgh initial equals a half mv final squared, not plus mgh final, because that canceled. What do they want me to get by itself? What do they ask me to find? Speed. Which one? Because I see 2 in that equation. Well, not even kinetic energy final. V final. They want you to get the V final by itself. And oh, I noticed something. What do you notice? How many of you been on a roller coaster? Okay. Keep your hand up if, before you went on the roller coaster, they made you step on a scale, carefully weighed you, and made sure that you weren't too fat or too small. Why do you think they didn't do that? Because masses cancel. This is why we don't have to go, oh, this is a fat person, let's put a small person in the car with them. We don't have to worry about any of that. Now, in real life, Jordan, there is a tiny bit of friction, so the masses don't quite cancel, but you build enough of a safety margin into your engineering, and for all intents and purposes, mathematically, the masses do. I don't know if you ever wondered if when you went on a ride, I don't know if you ever asked yourself, well, why aren't they having to be more, because we're going pretty fast, aren't they having to like weigh us or anything? Nope. So let's do that. Thunk, thunk, thunk. I end up with this. A half V initial squared plus G H initial equals a half V final squared. What are we trying to get by itself? I heard it here. V final. I'm going to pull out an equation solving trick. Do you see all the 1/2 fractions? I'm going to use Math 9 to clear fractions. I'm going to go like this. Times by 2, times by 2, times by 2. Those will cancel. Those will cancel. This 2 here won't cancel, but I still think it looks prettier. I'm going to get this. VI squared plus 2GHI equals VF squared. See it so far? Janaya, that should look familiar. Put your pencils down, look up. Remember that from Unit 1? VF squared equals VI squared plus 2AD? Remember that? VF squared equals VI squared plus 2. Oh, isn't G measured in meters per second squared in acceleration? And isn't that really a distance? I don't know if you remember, when I showed you this equation, I said, proving it is tricky, but it pops out of energy. Just popped out of energy. Oh, how to get rid of a squared? Okay, so final answer, V final is going to be the square root of VI squared. What's VI? I scrolled down. What was it? 12? Yeah. 12 squared plus 2 times 9.8, not negative, scalar, times 18. How fast will we be going at the bottom of the hill? 22.3?
No. Oh, yeah, 22.3.
Units?
Units per second.
Okay. Now that's if we were completely frictionless, and most roller coasters are pretty close. Pretty close. Because you think about how fast you're moving. If you stood next to a roller coaster, really the newer ones aren't that loud. If the reason they're not that loud is there's really not that much extra energy being generated into other stuff. Oh, and do they build them fairly aerodynamically now? So the whole air resistance passing your kinetic energy onto air molecules, there is some of that, not much of that. But suppose you were at the bottom with a radar gun and you noticed part B that at the bottom was only going 15 meters per second. Although theoretically it should be going 22.3. What can you conclude? Jamie, you conclude that some of the energy was lost to, I'll call it heat, to air resistance, to sound, to kinetic energy to the air, friction. We'll just call that all heat. How much? Is there a change in height, Jordan?
Yeah.
Is there a change in speed? Is it a wonky, curvy path? This is a job for conservation of energy. Cole, plus heat?
Yes.
Ah, yes. As before, are any of these 0?
Potential energy final.
Yeah, you hit the ground. Enzo, you did this one earlier. How would I get the heat by itself? That's what they want me to find.
Minus kinetic energy final.
Yep. It's going to be a bit of typing is all, but heat is going to be kinetic initial plus potential initial minus kinetic final. Whatever's missing must have gone into heat. Oh, and if it worked out to 0, then you would know that there was no friction. But I don't think it will this time. Well, I know it won't, because if it was 0, it would have gone at 22.3. It went slower. What if it went faster than 22.3? You've violated the law of conservation of energy. You got a perpetual motion machine. The universe is going to come crashing down and kill you. Right? Heat is going to be a half mv initial squared plus mgh initial minus a half mv final squared. Do the masses cancel this time? Careful.
No, these are
Ah. Is there a mass in this term? Yep. Is there a mass in this term? Yep. Is there a mass in this term? Yep. Is there a mass in this term? No. So in real life, your mass, Chris, does affect things slightly. But again, if I can get that heat as close to 0 as possible, then your mass hardly affects things. That's really why you don't need to step on a scale before you get onto a roller coaster. Otherwise, you'd have to. It's good engineering. I think we're going to get this then. The heat equals 0.5. What did I say the mass was? 255? 245? Initial velocity was 12, yes? Squared. Plus 245 times 9.8 times initial height was 18. Takeaway, at the bottom of the hill, we had 0.5 times 245 times 15 squared. Don't forget the squared. That's the most common mistake, by the way. Kids forget the squareds. How many joules were left over that must have gone into heat and sound and other bleeding energies? I don't know. Hang on. I think you're right. That sounded about right. How about 33300? Is a fairly easy way to remember it. 33,300? Ish. Joules. Track's got a bit hotter. How can we reduce friction? Grease. What does that do? Lowers mu, right? Yeah, but it lowers this. Because it can't change a normal force, can't change all that stuff, but hey, we can change mu, get it as low as possible. Number 6 is actually the same as 5b. Because in number 6, I'm giving you the initial height. Dropped, your initial speed is 0, so it's actually a little easier. Telling you the final speed, just like in 5b, I told you the final speed was 15. Find how much heat. Boring. Example 7. Oh, Tarzan! So let me ask. How many of you have ever taken a run at a rope swing, grabbed it, lifted your feet, and see how high you can swing? It's a great, or done it with a swing set. If you run and you belly flop into it, see how high you can swing as a kid. You've all tried these things, most of you at the playground. They're all great examples of conservation of energy. And again, Cole, the nice thing is, because energy is a scalar, we can use a sideways velocity, speed, to calculate an upwards height. because direction for energy doesn't care. Even though it's a yucky curved path, to try and do that with kinematics, with d equals VIT plus a half AT squared and VF equals VI plus AT, would be ridiculously difficult. We could. Ugh. So we got Tarzan weighing 82 kilograms. Ooh, Tarzan's putting on a little weight. He can run at 8 meters per second. He runs, what is 82 kilograms in pounds? Go 82 times 2.2. Huh? Oh, 108.4. Well, that's not too bad for Tarzan. Okay, I'll give him that. I thought it was a little higher. I guess what we're talking about is this. Here's your rope swing. He's going to run, grab and swing. Sean, is there a change in height? Is there a change in speed? Is it a funky, curvy path? This is a job for conservation of energy. Because the first couple that I did with you, Jordan, where we were launching stuff straight up, I'll be honest, I would have solved that, I think, using Unit 1 stuff, because it's quicker. But when you have a horizontal becoming a vertical, this is where energy shines. So, kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Plus heat, since it says maximum height, let's assume there's no friction. This rope is frictionless. Are any of these 0? At the top for a split second, I agree. Now this is where I sometimes have kids argue with me. They say, hey, Mr. Dewick, if he's grabbing the rope here, he's not on the ground where he's grabbing the rope. Here's the nice thing about conservation of energy. You can put 0 wherever you want. Let's put 0 nose level, because that's still going to give us how high he climbed compared to his eyes. Or if you wanted to figure out how high he climbed compared to his center of mass from his belly button, the distance is going to be the same no matter what we use as a reference, as long as we're consistent. So yeah, even though technically you could say, oh, he's not on the ground, I'll let 0 be the bottom of the rope. A half mv initial squared equals mg h final. Would this work if instead of Tarzan, I had Tantor the elephant running at 8 meters per second? I'd get the same answer, assuming the rope held. But mathematically, I'd get the same answer. Why? Masses cancel this time. How many of you have ever been on the wave swinger at the P&E? That's the ride. You sit in the swing, and it goes in a gentle circle, and there's some music. Right? It's right, you're near the main entrance. It's the tame ride. Right? It's called the wave swinger, I think it is. Okay? How many of you have ever noticed the empty chairs don't swing out further? They don't swing in closer. They actually swing out at the same angle as the full chairs. Do you know why? On that ride, what could you tell me about the masses mathematically? Turns out they cancel. Okay. Lots of that happens at amusement park rides. You guys, I never noticed that. Next, hey, if you go to Playland this summer, or if you take Physics 12, we'll be going to Playland as a field trip. That might be a ride you choose to analyze. Hey, what do they ask me to find here? Oh, I think that's going to be, I've seen this before, Mr. Dewick. VI squared divided by 2G. Cole, where'd the 2 come from? Yeah, from the front, yeah. 8 squared, that's 64, divided by 2 times 9.8. By the way, if you're actually, when I stand in line for an amusement park ride, I amuse myself by doing some physics. And so one of the things I always like to try and figure out is, how high will a ride get? I don't use 9.8 to do the math in my head. What's a nice number close to that? But really, if you want to figure out how high a ride is going to get, if you know its speed, square it and divide by 20, because it's 2 times 9.8. That'll tell you roughly how high you'll get. I kind of am curious. Now, the next question, well, how do you find its speed? Oh, there's all sorts of tricks of the trade where you can make some good estimations of that, too. Meanwhile, Tarzan or Tantor will reach 3.3 meters high. Okay. On Thursday, we're going to be doing a lab that's going to take probably about half an hour, and then I'm going to be assigning a bunch of these questions for you to try on Thursday. So you don't have any homework tonight. However, put your pencils down for a second, please.